Hi, my name is Sahil Sharma, and in this video we are going to study counters. These are the topics I am going to cover. First, I will discuss sequential circuits, in which the block diagram of a clocked synchronous sequential circuit will be shown. We will discuss the example of a sequential circuit with the state table and the state diagram. We will be designing a binary counter, in which I will be showing the state diagram and the excitation table, and also the K-maps and the logic diagram of the binary counter. Then we will be studying the counters of two types, asynchronous counter and the synchronous counter. In asynchronous counter we will be studying 3-bit ripple counter, and in synchronous counters we will be studying 4-bit synchronous binary counter. Sequential circuits. A sequential circuit is an interconnection of flip-flops and gates. The gates by themselves constitute a combinational circuit, but when we combine gates with the flip-flops, then it is known as a sequential circuit. This is the block diagram of a clocked synchronous sequential circuit. In this we give the external input to the combinational circuit along with the output of the flip-flop as the input to the combinational circuit. The clock pulse is provided to the flip-flop, and this combination will produce some output. Whole of this diagram is considered as a synchronous sequential circuit. So this is an example of a sequential circuit with state table and state diagram. So first we see the sequential circuit. In this we have two D flip-flops. Along with it the clock signal is provided, and the combinational circuit above and combinational circuit below have been provided. This combination of combinational circuit and the flip-flop with the clock signal is known as sequential circuit. Let's see the state table for this diagram. If the present state of A and B is 0 0 and X is also 0, then the next state of A and B is 0 0 and output Y will be 0. If we input all the values here of the present state and the input, we get these three values as the output. Similarly, for inputting 0 0 1, we get the value 0 1 0. Whole of the state table can be verified by inputting values into the sequential circuit and verifying it for the output values. Let's focus on the state diagram. The binary number inside each circle identifies the state of the flip-flops. The directed lines are labeled with two binary numbers separated by a slash. The input value during the present state is labeled first, and the number after the slash gives the output during the present state. For example, the directed line from state 0 0 to 0 1 is labeled 1 0, meaning that when the sequential circuit is in the present state of 0 0 and the next input is 1, the output is 0. After a clock transition, the circuit goes to the next state 0 1. The same clock transition may change the input value. If the input changes to 0, the output becomes 1. But if the input remains 1, the output stays 0. This information is obtained from the state diagram along the two directed lines emanating from the circle representing the state 0 1. A directed line connecting a circle with itself indicates that no change of state occurs. So in a binary counter we want to do a counting from 0 0 to 0 1, then 1 0, then 1 1, then again to 0 0. So this is a 2-bit binary counter in which we are counting from 0 to 3 and then coming back to 0. This binary counter needs two flip-flops A and B to represent the 2 bits. The diagram is drawn to show that the states of the circuit follow the binary count as long as X equal to 1. So every time when X equal to 1, then the counter increases. The state following 1 1 is 0 0, which causes the count to be repeated. Let's see the excitation table for the binary counter. The first 5 columns of the table, AB as the present state, X as the input, and AB of the next state, constitute the state table. JA, KA are the JK values of the flip-flop A. JB and KB are the values of the flip-flop B. Both the flip-flops are of JK. we can use the excitation table for JK to predict which value of your J and K will come when the present and next value are being handled. So using this excitation table, when present and next state of flip-flop A are same as 0 0, the value JK will be 0x. So JA and KA are 0x. Similarly, if the value of flip-flop B has a present state of 0 and next state as 0, then again J and K will be 0x. Let's verify some other value. When the present value of A flip-flop is 1 and the next state is also 1, so using this excitation table, J and K value are x and 0. X is don't care value. So x and 0 are the value of A flip-flop. Similarly, we can verify at some other place. When B is the present state and 0 is the next state for the B flip-flop, then what will be the value of flip-flop JK? Because we are seeing the B flip-flop, the values will be x and 1. Using this table, we can see that if present state is 1, next state is 0, so this is the third case, it will be x and 1. So don't care and 1 for the JK. So here it is. So this is the K map generated based on the excitation table seen earlier, and using this K map we can design this logic diagram of binary counter. So what are counters? A counter is a register that goes through a predetermined sequence of states upon the application of input pulses. These input pulses may be clock pulses or may come from external source. Counters can be realized using the flip-flops with the complementing capabilities. T and JK flip-flops have the complementing capability, so the counters can use T and JK flip-flop. A counter counts a sequence of numbers depending on the number of clock pulses received. Counters are of two types depending on to which flip-flop in the counter circuit the clock is applied: asynchronous counter and the synchronous counter. If there is a n-bit binary counter, it has n flip-flops which will count in the binary sequence from 0 to 2 raised power n minus 1. What is a asynchronous counter? In a asynchronous counter, the clock pulse is applied only to the first flip-flop. All the other flip-flops are clocked by the output produced by the preceding flip-flop. Asynchronous counters are also called ripple counters because the clock pulses appear to be rippling their way through the flip-flops. Now let's see 3-bit ripple counter and its timing diagram. Because we are talking about the asynchronous counter, the clock pulse is only given to the first flip-flop. So this one is the first flip-flop. How do we know this? Because this has the Q0 as the output, this one has the Q1 as the output, and this one has the Q2 as the output. So the first flip-flop is this one. We apply J and K as high values initially. When both are 1, the complementary value is calculated. If J and K is 1, Q is 0, so Q bar is 1. So this clock pulse is given here, and these two are values again high, 1 and 1. This is 0, Q bar is 1, so again clock pulse is given here. We can see here that clock pulse is given to only the first flip-flop, and all the other flip-flops have the clock as the output from the previous one. Let's see the timing diagram of the 3-bit ripple counter. Observe that the first flip-flop's output Q0 changes at the rising edge of the clock. So when clock is rising from 0 to 1, Q0 changes. The second flip-flop's output, which is Q1, changes on the falling edge of the Q0. So this Q1 is changing every time at the falling edge of the Q0. So here it is falling from 1 to 0, Q1 is changing. Again here Q0 is falling from 1 to 0, this Q1 value changes. At this place also, when Q0 is changing from 1 to 0, again the value of Q1 changes. Similarly for Q2, the value of Q2 changes at the falling edge of Q1. Every time Q1 edge falls, the value of Q2 changes. It can be observed here also in these two values. Also at this place, when Q1 is changing from 1 to 0, when it is falling, So Q2 is also changing. If Q2 was 1, it becomes 0. If Q2 was 0, it becomes 1 at the falling edge of the Q1. So synchronous counters. Synchronous counters are having a common clock. So in the 4-bit synchronous binary counter diagram, you can see clearly that this clock pulse is being shared with all the 4 JK flip-flops at this point, at this point, this point, and this point. So the C inputs of all the flip-flops receive the common clock. So this was the common clock. We can see here this binary counter has A0 as the LSB and A3 as the MSB. The output of first flip-flop A0 is connected with the AND gate and the count enable value for the second flip-flop, and this continues. The output A1 is used for A2 input, then A2 value is used with AND gate for the A3 input, and the final output carry value is calculated here. When JK value are 0, there will be no change at the Q point. If J and K are 0, 1, this Q will be 0. When J and K are 1, 0, this Q will be 1. And similarly, if both J and K are 1, then this Q will be complemented. These are the references. Thank you for watching.